material, or what we call material, which is a set of things that we're going to put in, and you're going to receive only one single email for one time of uploading. But we cannot avoid uploading multiple times for each lecture. For example, we can upload most of the slides and videos in one, and then maybe we have to upload a lab later, or some additional. But for sure that the amount of emails you're gonna get there is going to be greatly reduced. So so today is data prep. So you have the lecture, and you have you have a pre-assessment, and you already went through. So you want to do all these lecture 3 slides selectively, and then you're gonna go through 10. We'll go through the lab 2. And all these things are just supporting materials. Hopefully, by reading all these things, will help you understand 100% of the slides. Okay, that's the purpose of flipped classroom. So, any question? You can ask question in Vietnamese if you want to. I realize that sometimes it's best to communicate in Vietnamese, so maybe some of the procedures we will speak Vietnamese just to help. We want participation, right? So we don't want just a quiet class. Đó, mọi người nếu mà không có nói được tiếng Anh nhiều, có thể là hỏi hoặc là trao đổi bằng tiếng Việt cũng được. Nếu mà làm như vậy nó làm cái lớp sống động hơn. Chúng tôi không có muốn chỉ lớp mà ngồi nghe thôi, mà mình muốn sẽ qua lại rất nhiều. Và nếu mà làm như vậy thì học hành nó có dễ dàng tiến bộ hơn. Tại vì nếu mà học mà mình không hỏi là nhiều lúc mình không hiểu thì cũng ok thôi, nhưng mà mình tương tác với nhau thì càng tốt. Do đó là tuy là cái lớp muốn dạy bằng tiếng Anh, nhưng mà có thể là khi mình dạy tiếng Anh rồi khi trao đổi có thể là dùng tiếng Việt cũng ok. Đó là suy nghĩ của tôi. Mọi người có câu hỏi gì về cái hình thức học không ạ? Hình thức nhất là hình thức flipped classroom. Thì cái này nó không hẳn là 100% flipped classroom, tức là cái về cái bài giảng chúng tôi không có ghi âm, tại vì cái đó nó đòi hỏi rất nhiều công sức, và nếu mình muốn làm đúng thì bây giờ chúng tôi dùng những cái video hiện tại có trên mạng, và những cái video bởi những người dạy rất là giỏi, giống như Professor Adam Tiemann, ông đó, ông người Do Thái, ông bên kia, ông những cái bài giảng của ông rất là có giá trị, thì mình dùng ông giống như là mình mướn ông để dạy vậy đó. Thì mọi người học viên thì nên tận dụng những nguồn lực đó mình học để cho hiểu. Cái gì mình không hiểu thì mình coi, còn mình hiểu rồi thì mình khỏi coi. Cái chương sống của cái chuyện gì mình cần biết là trong trên những cái tài liệu PowerPoint, những cái PDF, cái slide đó. Okay.
Phil, may I add in at this point to remind everyone, in your Zoom controls, you have reactions, and two of the reactions that you can give are to speed things up or slow things down if you're having trouble understanding. So be sure to use those reactions, because then we can have feedback for our instructors, and our instructors can adjust appropriately based on the flipped classroom.
Yeah, that's great idea. And please, when I'm teaching, I don't see a lot of reactions. So instructors and TAs, if you see them, please remind me via voice. And also there are raise hand, reaction too. So if you want to speak, you can raise your hand. Right? Ok, thì hy vọng mọi người dùng những cái đó để mà có thể là tương tác cũng được. Nhất là giơ tay để mà xin câu hỏi. Còn nếu mà không có hỏi được giơ tay thì viết trong cái chat room, viết trong chat những câu hỏi, khỏi tiếng Việt hoặc tiếng Anh thì cũng được. Thì đa số những cái người phụ giảng, những cái instructor khác, người ta sẽ trả lời trong đó. Mà nếu mà trả lời không được hoặc là muốn trả lời cho cho hữu ích nguyên cả nhóm thì có thể TA có thể nói cho tôi biết và người đang giảng sẽ lặp lại câu hỏi và trả lời chung cho cả lớp. Ok, thì mọi người cố gắng tham gia nha, còn không tham gia thầy giáo ngủ là coi như là không có ai dạy. Right. So let's go right to it.
Mày thoát cái này luôn, mày vô lại thoát luôn.
Thieng, are you here? Oh yeah, you're here. So I'm going to go very quickly, Thieng, and you can take over with labs, right, Thieng?
Yes, I'm here. So
okay. So I'm based on the survey. I'm going to just pick and choose a few things, and then hopefully you have plenty of time to start with the lab. So let's see. Oops. Okay. So design import. So just an overview, right? This is the import step where you have different components to read in. The purpose is to read in all the necessary inputs and to check the quality of the inputs, right? To make sure that whatever you feed in are valid and the constraints are accurate. Okay, so and then the final purpose is the design is ready for the next step, which is floor planning. So you check the quality of the input. So the input have a few set that first of all the gate netlist and also the abstracts, the technology files and interconnect technology files, and then you have timing information and physical constraint information. Right? So netlist import, most of you already know. So in here, when you receive the PDF, you can click on the PDF and you can just go in. When I'm here, I cannot go in. Okay, yeah, you can go in and see. So the gate level netlist is generated by the synthesis step. Right, so it went from RTL code, which is like commands here, into the structure gate level netlist where you see ands and ors and all everything. But this one will meet timing, but the RC are estimated, and the clock skews and clocks are ideals, and the clock skews are estimated, and parasitics are estimated. So this is the input to the place around. Okay, the netlist will look like the netlist coming out of place and route and mid timing, but again, clocks are ideal and parasitic are estimated. Okay, so so there are different.
This meeting is being recorded.
Okay, thank you, Dave. So the file format is Verilog or the VHDL and all. So these things you can read, but basically it is read in with the command called read netlist. So you use this command to read netlist, the get netlist going in. Okay, so and then the cell abstracts. So everything is the cells are standard cells memories of the IPs. Formats are left basically, but they are all other format. And you read in with the read physical. So just a reminder, your input coming from different places, from front end design where they design the RTL, go into the back end. That from Foundry where all these technology models and tech files come in, and the external IP vendors where you buy the IPs and then you integrate into your SoC or your design, and then any internally developed IP. So you read the physical abstract with this command called read physical, and you read all these left. Okay. So and then timing constraint have a whole bunch of files, but most important thing is the MMMC file that has different different components to it. And sorry for the animation, but the first one is the library set. So this one, the major components are timing models. You want to specify what timing models are used for what PVT. So the typical PVT is the N channel, slow N, slow P, minimum voltage and maximum temperature. This is the corner where the transistors are slowest. The gate delays are the maximum, and there's another corner where the transistors are very fast and the voltage is big and the temperature is low. And these tend to be on the fast corner, and you know why this is important. So the first one is important for setup, and the second one is important for hold. And they are typical. Usually, sometimes you do power consumption at this corner, so everything is nominal or typical. So that's a library set where you say where are the timing model, and then the constraint mode with all these different modes in your block in your design, like functional or you scan mode, test mode, everything. There's just the operating mode of the chip. And then for each operating mode, you have a delay constraint called SDC, a standard delay constraint or synopsis delay constraint. So this one you can click on YouTube link and you can understand all the details of it. And you going forward, you need to learn how all these different things are called. Like what is a design, what is a port, what is a pin, right? What is an instance, what is a net, right? And what is a module. So you need to learn all these things so that when you process a database later, you know which one is which. Because when you put a constraints or want to do something, there's always an object that you referring to in your design. So you need to make sure that you understand the naming conventions. And so that's the second part of your MMMC. The third part will be RC corner, right? So the RC corners are where you have the maximum RNC or where you have the minimum RNC. So with the modern extraction, we have temperature as part of the extraction as well. So RC max 40 degree C might not have the capacitance as big as RC max 125 degrees C. So you have different corners because this is represent the process variation on the pin caps or on the wires. So you want to make sure that certain corner you are analyzing at the right corner. For example, you set up when everything is low, you want RC to be big so that you can model the worst case delays. And when you're analyzing whole, when everything is fast, you want to put the RC min in your what you will learn as analysis view for whole. Yes.
Hình như thầy đang giảng cái lecture 4 đó thầy. Cái hôm bữa thầy gửi là cái lecture 3.
Cái này lecture 4 hả?
Dạ.
Chết cha, xin lỗi. Sao không nói sớm? Xin lỗi. Cái này là lecture hôm nay mình dạy lecture 3 hả?
Đéo đứa nào nói. Không nói. Dạy đéo hiểu gì luôn mà.
Nobody caught that. Okay. Lecture 3 mà mọi người hiểu là chắc mọi người cũng siêu đẳng lắm rồi. Xin lỗi. Okay. Ủa vậy là cái okay. Yeah, lecture 3 là data prep. Is it correct, Thiên? Yeah, today is lecture 3. Okay. Thì mọi người có câu hỏi gì cứ lên tiếng nha, còn mà giơ tay thì TA xin vui lòng cho biết. Thì data prep thì cái này mình cũng nói xong rồi, synthesis còn mà text file thì cái này chắc mọi người cũng biết rồi. Thì text file nó có những cái layers, mình define mấy cái layers, hoặc là mình define mấy cái design rules, hoặc mình we define the units and other antenna details, etc. And one of the things you're defining is the site. The site is a unit cell that define the rows. A site is a unit, right? So it has it's at the same height. A gate can be multiple of a site. So this one is a site. It's a size 0.2 by 12. That means that 12 micron is a height, and then 0.2 is a unit of a standard cell is a multiple of this 0.2. So it's called a site called core. So you see in here a horizontal grid and vertical grid. These represent the I think the wiring tracks, and the cell origins right here. So the technology file, the left file define how many layers and everything, and in here, it described that. And then interconnect technology file is used for mainly the extraction, and is also read into the placement route for RC. Each of these engine has its own RC extraction. This is a sign off, but placement route has its own extraction as well. So this is an interconnect technology, for example. So it just lists all these different layer stacks, right? So it has for meta 1, and it goes to what they call MX, meaning the intermediate metals, and then they have thick metal, and then ultra thick metals, and AP, etc. So in a technology file, it defines all these different characteristics, and the design, the extractor will base the information provided here, and we'll use it to extract the parsec of a design. So the IPs, you have different IPs: standard cell, IO cells, custom macros, and in here you have the different rows defined by the site. So when we see 12 microns, the 12 is the height. And then you can have multiple height, one cell can have multiple height as well, and IO cell has a different height. And so this one, everybody know about the level of abstractions, and this is the physical abstraction, where you have the full layout, and then you just extract whatever the place around need. So in here you can only see just the metal, because the place route will route to this pin only, and it ignore diffusion poly underneath here. It doesn't need to see when it's at the place route. So it's just hide. It's just one of the methodologies. Just hide the information underneath for faster runtime and for
Không biết mang vào đây có dùng không? Mà để cho hay là bán cho đồng nát thôi? Anh cũng mang vào đấy. Nếu mà cho thì mang vào đây.
Dave, can you mute that person? Okay, so Còn cái này là timing abstraction thì nó các cái data clip thì main thing là they have delay arcs and constraint arc. Right? Delay arcs are really what is the delay from one pin to the other, a delay from one pin to the other. So those are delay time, and constraint arc are set up and hold constraints. And I think you guys got that. It's easy to understand. So the nonlinear delay time model are the two-dimensional models that have a slew rate, input slew rate, and output net transition. So you have this table, it's a lookup table. So when the delay calculator has the input net transition and it has all these RC, the RC will include the wiring and then the pin cap of the next guy. So based on this information, what they call a delay calculator will look up and say, okay, I have a slew rate of what is this? 1002. And I have a output cap of 1002 here. So my delay is this guy. But if I have 1002.5, then I interpolate between these two numbers. And I'm going to, it will calculate the exact number. Right? And then we have current source model. So this is not nonlinear delay model, meaning that the delays are nonlinear, but they still based on points. In here, the current source model, to understand it simply without going through much detail, is basically the driver model, right? The driver model on CCS, it captures the current flowing through. And the ECSM, which is a cadence format, that capture the voltage, but basically it's the same data. One look at the current, one look at the voltage. The nutshell is that this one allows you to be more accurate in between 2 points. For example, if your voltage of 0.9 and then you go to 1 volt, if you 0.95, you have a delay that's really very accurate versus a lookup table. It's really actually simulation based. So the current source models are known to be very accurate and support dynamic voltage scaling, as you can know later when you control the voltage to control the power and the speed. So you don't have a fixed voltage, but you play with the voltages. So if you do that and you want accurate timing, then you use this current source model. So nowadays, people use current source model and not so much on NLDM, even though some of the IPs might still have the NLDM. But when you see a current source model, CCS or ECSM, you use them versus the non-current source because they are more accurate. A physical constraint at this point, at the chip level, you just define X and Y dimension. You learn how to do that in the next step. And then in the import step, the only thing you're controlling is the location of the IO paths. So you feed in a placement file, and the import step will place your IO cells according to your file. So you learn that in the next step. But if you do at a block level, then when you read in, you need to have a way to define what we call here is PR boundary. This is the chip, right? You have PR boundary. You say, where do you have all these standard cell place and all your digital placement route done? That means that when at the result, after you finish, you have this block, and then you plug in this chip. So that at this point is only the constraints are just a PR, mean placement route, the boundary, and the pin locations. So in summary, the data prep, this step doesn't teach you how to do the prep, but more of understanding what the different things that goes into the import step. And like I say, import step is the first step that we'll do to before you do floor planning.
So
yeah.
We have a couple of questions that have come in the last 5 minutes. The first one, let's see. In the video you give us, there are two kinds of LEF files, LEF and tech LEF. Do they have any connection or specific information between them that we need to know?
Okay, so technology left and cell left. Okay, so let's do that. Okay, so technology left. This is the example of the technology left. So technology, so technology left, as you can see, there's no NAND gate or NOR gate. It just say, okay, what are the units? When you read a number here, right? When you read the number width, you see just a pure number. What is the unit? And here it will tell you what the units are. So current is in terms of 10,000 milliamps, and voltage is 1,000 volt. I might be wrong here. Tim is more up to date on these, what it means. But basically, via here you will know what this number translated into milliamps or into microns, right, or anything. And you can see this manufacturing grid. This is the final, the finest resolution that you have on your layout. And then we mentioned about the site core. This is a unit of your standard cells. That we'll go over that the other left. So basically, say, okay, in this technology file, there's layers. So after layers M1, so you have a bunch of layers. So you have an exercise to where you look. Tien will tell you, hey, go look at this left file and tell us how many layers are there. How many metal layers, right? As you can see, the metal stack can be you can route from metal 1 to metal 6, for example, or some places you can route from metal 1 to metal 10. So you look at this tech file, then you see the layers. So you will know how many layers in the tech file, and you have the design rules. So it has nothing to do with the cells, right? You have antenna information, you have via information, etc. And you have something called generated vias, but you're gonna learn this one later. So basically, the tech left are related to, as the name indicates, right, technology, and the other left are. Do I have a left file for the standard cell? Yeah, over here. So this is the other left file. You see cell abstract left. So this left file are specific to the gate, like an inverter gate. In this case, a NAND 1 gate. So in here is to say there's a site. So this is a unit unit cell. That means that the width of this one is a multiple of width of here, and here is 0.14 is the minimum, the base. So this 9.1 have to be the width of it has to be a multiple of 0.14, and 0.9 is the height. So every standard cell will have 0.9, right? And here you see each of these a macro NAND 1, right? So the class is core. So class core relate to this site, right? So sometimes in a design you have multiple cell heights. Some of them you have maybe another standard cell libraries that have another class that have a different units tile. So on here it will show you the size. So the origin is always 0, 0 is right here, and size in here you see this 0.56 by 0.9. You see 0.9 is the height and 0.56 is the width, and this 0.56 better a multiple of 0.14. And then it have symmetry, meaning can it rotate X and you flip X and Y? Sometimes you cannot flip the cell, for example. So all the physical physical characteristic of it. And then you have a description of pin, and here's pin Y, right? It will say there's some antenna information at this point. You don't need to worry. And then it is an output, and it is a signal versus a power or something else. And in here, say port, that means that port, you can find out this port is really the input output. So say in this port of this pin Y, there's a layer. This layer is in M1, and it has all these rectangles. So drag will maybe 1, 2, 3 rectangle that make up this pin. And so pin A have something here, pin B have something there, and then BDD is a power, and then ground as here, and it has here it's called OBS, mean obstruction. It's not a real layer, but say, hey, block, don't let this layer go through certain shape. So this is so very good question. Those two, I hope I answered the question of what the differences between the two. So you have this cell lab for every cell in the library. If you have 900 cells, you have 900 of these. Okay.
And Phil, there was a follow-up to this question. The tech left comes from the manufacturer. Is that correct?
Tech left, yes, come from the fab. Yes. Yeah.
Okay. All right. So other questions here, and we're about 45 minutes into the hour. In your pre-assessment, you mentioned layer metal 1 and layer metal 5 in physical abstraction. What is the difference between these two layers?
Okay. So so let's see, where's the metal stack? Okay, over here. Over here is a typical metal stack. In this case, it's a 22 nanometer. Right, has metal 1 is the lowest level. So metal 1 usually, you can see in a standard cell, metal 1 is used for internal routing of the cells, right? And metal 1 used to be is the thinnest, and it is the the most resistive, meaning that the R on the metal 1 is really high. So it's used for but it can be fine, and it's thin, and it's designed for cells. So that's the metal 1. So that's the lowest level of metal, and metal 5 is here. So up on metal 1 will be metal 2, metal 3, metal 4, and they are connected via vias, like V1, V2, V3, and all the way to metal 6. In here you have metal 7. And metal 7 now is what we call Y. So in here you say MX. So this is the term that TSMC used to indicate X type of metals, meaning that it has certain characteristic of R's and C, that these are used for routing, and metal 1 is used for internal cell routing. So metal 1 and metal 2 are very different, meaning that metal 2 can be lower resistance than metal 1. But when you go to metal 6 in this process, you go into what you call MY. MY is really a thicker metal. A thicker metal allows you to have less resistance. And for fast signal, you route on the high layer, and here you have two Y layers, and over top in here you have another one, is ultra thick, I think. So these are metal 9 and metal 10, and they are much thicker, and they lower resistance, but they can be used for power grid, etc. And then you see in here there's the IP, AP layer. So this one is the highest level. When you look down the chip, you see AP and all. So to answer your question, is metal 1 is thinner and higher resistance than metal 5. In here, metal 5 and metal 4, metal 3, they are the same. So in the question in the when you have a standard cell, you usually have the lowest layer on the standard cell because you need to route on top of the standard cells. So so in most cases, for older technology, only metal 1 is used, but in 22, for example, metal 2 are used. So but you don't see higher layers in a cell. So that's why metal 5 is not the right answer. So I hope I hope I answered that question.
All right. If you have time, the next question was, can you elaborate more on why CCS is more accurate than ECSM if they contain the same information?
Yeah, that was a trick question. CCS and ECSM supposed to be in the same. It's a very good question. It's the same quality, but the question in there you can see ECSM. So I throw in an S there. So ECSM is not a timing model. But in terms of if you compare between the two, they're the same quality. One look at the voltage and the other one look at the current. So they have the same, even though CCS have some advantages. Even Cadence use CCS. So if you have a choice, you still want to use CCS.
And another student is requesting elaboration on what does RC mean in the RC transition or the RC tech file.
RC transition, RC tech file. So RC generally means R and C mean resistance and capacitance. So they are parasitics. They are really the present in the wiring. So you can see the metal wiring. You go from pin A to pin B. Let me see. Wire delay. All right. Okay, over here. See when we have a gate driving a wire, right? So for say this gate is far away, right? And so you have
transition là
you have a gate.
tụ chở trên nét, tụ chở trên
Why when I need it always a problem. This is weird. Maybe I just do.
Tao ngồi liên 2 tiếng là nó sẽ báo.
So when you have a gate, this is the inverter 1.
Okay.
And then the other gate you see is far away, so you wire them, right? So you have pin Y here, and you have the wiring. You go through your design and you go into a pin on this inverter 2. So when you do that, you have R and C along the way.
Anh nói RC transition là chở cán trên
đường slow
dây.
now. Okay.
Chở
so each of these wires are R and C, right? So your delay will have a delay. The intrinsic delay, the delays due to slew rate of the input, and delays due to the wiring, right? And then the delay. So your delay, when you have a signal going here, it will have at this point you have so sorry. You have a reverse, right? So at this point, at the output, you have certain, say, this is A. So you have from input to A, you have certain delay. And in order for the signal to reach from A to B here, it will have a wire delay. this is wire delay. This is what you call RC delay. Before this signal, so this inverter will receive the signal at this point, not at this point. So the intrinsic delay, the RC delay, that add to it. But I don't know what we call RC transition or RC tech file. Or RC tech file is something different.
All right, and then the final question that's in the chat room is, please explain more about SITE, S-I-T-E, and show us where it is located in your pictures.
Okay, right. So let me address the tech file. So,
okay, I'm sorry.
So the tech file, yeah, no problem. Yeah, the interconnect tech file in here, it will. So in here you see conductor, right? M1, for example, over here, it will tell you the thickness of M1, the height, and the wire, different physical information, and also it has as RHO, meaning sheet resistance per unit, and it has different values for to describe the conductor, including including the fuel oxide thickness. So as you can see, know the capacitance is dependent on the thickness of the oxide, fuel oxide in between them as well. I have a picture of what is that, maybe in another view. So basically, a capacitance. Try again to draw. So if it is a wire here, you have a capacitance called parallel plate capacitance. You have fringing capacitance that to the ground, and also the coupling capacitance. If you have another metal in here, you have you have coupling capacitance to the neighbor. So all these capacitances, in order for you to go from the physical to the SPICE netlist, where you or where you calculate the delays from based on the RC networks, you go the extractor tool can tell you. The extractor tool will have to look at all these unit value, right, and all the value specified in here and all the place, and based on these metal stacking, it will give you from physical, from layout to R's and C's for your calculator. So that's the RC tech file. This is the RC tech file. And the unit tau. So let's go to unit tau. I wish I have a picture of unit tau. So this is, if you think about, this might be a unit tau, but this not. So unit tau is very thin. So it look like it's a gauge. So unit tau will look like this, but very thin. Represent the unit. And everything is built off this unit. For example, before we say 0.14, right? And this one might be 0.56 in the other example. Right, so this unit tau, this line in yellow represents, say, this unit tau base is created in the technology lab. And in technology lab will tell you, okay, say, I think this might be metal horizontal grid. Just think this is metal 2, for example. In the technology file, it say metal 2 tracks, meaning the router is a track-based router. So the router will route metal 2 on this grid. This will be a guidance. So the site will have metal 2, say, all the metal 2 and look like this. right? And then meta 1 will be vertical. So it's a different. Say, for example, it say meta 1. I'm going to define from here. So the site will have a track, say meta 1, which is offset. So it will define what is where do you have the meta 1 tracks, and these are site, and then this site is used to build all these NAND gate, NOR gate. They get the tracks and they get all the information from the site. And if you look at the
Few quick reminder, it's almost 9 o'clock. So
okay, I think I'm gone enough for that. Okay, anything else?
Phil, the final question was, can you please explain more about the site, SITE, and show us how and where it is located in the picture?
I
Yeah,
think I answered that.
right.
So we're gonna do that in the lab. So
Okay, all right, good. All right, I think it's time for a 5-minute break and then go back and we'll do the lab.
All right, we'll start back up at 10:05. I'll have a clock going on the screen for everyone. Please be back and ready to go about a minute beforehand. Thanks.
All right, thank you.
chữ là đéo thấy hai không hiểu nhiều. Nãy không nói là đợi phòng học lớp 4 này. Gì đấy mẹ lại đúng không? Mày ngồi đây đúng không? Mày đi trước đi.
Phil, can you stop sharing?
I'm trying to look for the button, but you can share and then I think you override. Yeah.
Trời ơi, không hiểu gì hết.
Okay.
And Tina, did you want a timer up, or I can just give audio announcements?
Em bị nói chung
Yes, you.
máy em nó nhỏ xíu
Let me
rồi,
see.
không có dùng được
Yes, I think for now you can do the.
Coi lại.
Yeah, I think that's good. I'll just prepare what I need to share here.